Okay, welcome back, grade 12s. It's time for our third and final section on more optimization questions. These are to a specific category called DVT questions. They will always involve two vehicles, whether they're cars, trains, bikes, boats, or in this case, people running. But the key that connects these kinds of questions, it's motion of two different vehicles, two different people, and the motion is carrying them in perpendicular directions. In other words, one person is going north or south, and the other person is headed east or west. And that is the idea that links these kinds of questions together. And so there's common characteristics, which means that we have to sort of follow a typical approach, and then you know what to expect in the variety of these questions. So as I begin a question, this is straight from the textbook, but it was a good example. So I copied it from the book. I'm going to do it for you. I'm going to point out a few things, but I'm going to begin like I always do. I make a really clear diagram with all of my variables included on that diagram, and that requires some interpretation of the question. Now, the one thing that's going to be common for all of these questions is the motion of these objects. They will start at the same time and they will stop at the same time. And so I will always let T represent the number of hours, in this case, because the units are kilometers per hour, that they are in motion. So that's always going to be a variable that I'm going to use in every DVT question, okay? And then I sketch it. So it says Ian and Ada are both training for a marathon. Ian's house is located 20 north of Ada. So I draw this as Ada's house, and I draw this as Ian's house, and we know this entire distance is 20 kilometers. That's due north. It says at 9 a.m. one Saturday, Ian leaves his house and heads, that's supposed to say jog, not hog, and jogs south. And Ian is going 8 kilometers per hour, right towards Ada's house. At the same time, Ada leaves her house, but she's jogging east. And her speed is 6 kilometers per hour. It says, when are they closest together? So, and it says, given they both run for 2.5 hours, which we'll talk about in a minute. But if I said, Ian, if I'm in a helicopter flying over this and I say to them, they have microphones in their ears, on your mark, get set, go, boom, 9 a.m. they take off. And I in the helicopter can see that what the distance would be between them. For example, if Ian was at this point and Ada over here, this would be the distance. But if they ran a little further, this would be the distance between them. So you can see that at different points in time, that distance between where they are is constantly changing. So I'm going to erase this. And I'm going to say, imagine this scenario, because it lets you visualize what's happening. You're in a helicopter flying above, so you can see them both very clearly running. And you're measuring the distance, the constantly changing distance. And you see that sweet moment when, whoa, right there, they're never going to be closer than that. So you yell into the microphone, freeze. So let's pretend Ian gets this far and freezes, and Ada got this far. Of course, it's not quite realistic because he runs faster than her, so his arrow probably should be a little shorter, but doesn't matter because we're going to go by the numbers and the variables that we put. So imagine that you're in the helicopter, yell freeze, and so they stop running. Now you know that T will be less than 2.5 hours. That's one reason why they give this. I'll explain more about this later. In most questions, you won't even have such a fact, but in this case, I'll give you the reasoning why. Before we do that, let's assemble our information. We're using the relationship that distance is velocity times time. I can assign a variable that indicates the distance that Ian actually ran in that time until he was yelled at to freeze. Because he's going 8 kilometers per hour, and we're letting T, lowercase t, be the number of hours. And so he will have actually run 8t kilometers. Similarly, in that same amount of time, Ada will run 6 kilometers an hour for t hours, and we get this. The way you solve all of these questions every time is in this format. You make the 2 arrows and assign the variables for distance. You then create a right triangle, and that's the essence of the question. Now, the only way I'm going to get these guys involved in a right triangle is if I go all the way to Ada's house, and then I connect the 2 arrowheads. So this is the distance that I'm trying to minimize. This is 6t. This is a right angle. I would love to have a variable right here so that I would have a triangle. And if I have the t's in here with the d, I can create the equation of constraint, or really the equation of connection, as I like to call it, or the actual equation of what we're minimizing or maximizing. The trick is to get variable representing this part, which I'll write in red. And of course, you see, if the whole distance is 20 kilometers, because that's how far his house was, and he ran 8t, then the distance that's missing is 20 minus the 8t. And this triangle is going to give me my equation. So when you do these questions, they're just slightly different from the standard ones that we have been doing. Because the equation of constraint and the equation of what you're trying to minimize, it's all here. It's basically, you're trying to minimize d. You don't need an equation of constraint or connection because there's only one variable. And the connection, what we're trying to minimize, d, it's Pythagorean theorem. That's the equation of what you're minimizing. Again, there's no equation of constraint because there's only one independent variable. Basically, this is the equation that we have to minimize. And that means this is the equation, the expression that I have to get the derivative of. So again, there is no equation of constraint because we have the equation of what we're minimizing in one independent variable. And the equation is always Pythagorean theorem in these examples. And your task is to create the right triangle and assign variables to the sides of the right triangle. The distance will always be the hypotenuse, and you'll always have an equation that looks similar to this one. Now, to get this derivative, I'm going to simplify this first. I'm going to square this out, so I get 400 minus 320t plus 64t squared plus 36t squared to the exponent 1/2. Watch out, don't forget to square the coefficients as well. And then when you collect like terms, you have an expression which is going to be pretty easy to take the derivative of, but something's going to happen here that hasn't happened before. When I take the derivative, I'm forced to do the chain rule. 400, the half comes in front, you leave the base the same, you drop the exponent by 1, and then it's the derivative of the inside, the derivative of the base, which looks like this. And then, of course, we know we set the derivative equal to 0. Now, this is the same. One of the things I like to emphasize is every time we do these, hopefully all the times that you've been doing this for all the other homework questions, you will have negative exponents, but remember the trick was to multiply by that exact same expression, a positive exponent. Now, this is all one term. So if I multiply this expression by 0, I get 0. And if I multiply this expression by this, the negative 1/2 plus 1/2 is 0. So the product of this with this entire right side is simply that big, ugly expression with the negative exponent basically disappears. It's not the only way to solve these, but it's the way that I've been instructing you to do really from the first video right through. There's always negative exponents. I always multiply through by the positive exponent. Problem solved. Transpose the half by multiplying both sides by 2, and it disappears. And then you bring the 320 to the other side, and pretty quickly and pretty easily, you've solved for t. 16 over 10 is 1.6. Now remember, t is hours. So what it means is in 1 hour and 36 minutes, they run for, they stop. You can figure out the exact distance that Ian would have run by going 1.6 times 8. The exact distance that Ada would have run would be 6 times 1.6. And so let's see what those distances are. 1.6 times 8 is 12.8 kilometers. 1.6 times 6 is 9.6 kilometers. And if you have a right triangle, where this is 9.6 and this is 12.8, it would be a pretty simple task. Sorry guys. There's their velocity times time to get their distance. This is the distance Ada ran. This is the distance that Ian ran. And it's simple to find the D, if you needed to find it, to know what that minimum distance is, simply by taking, Pythagorean theorem. But the question doesn't even ask that. The question specifically says, when are they closest together? Now be careful, it's after 1 hour and 36 minutes of running. That's when the distance between them is a minimum. But because they left at 9 a.m. in this situation, what time is asking you what time of day? So the time of day would be 10:36 a.m. That's 1 hour and 36 minutes after they both left. At 10:36 a.m., they are closest together. Now, that's the other reason why you want to have this 2.5 hour piece of information. Because if you had solved for t and it was greater than 2.5, you would know that you made a mistake. There is another point which you may find confusing, but I'm going to demonstrate it nonetheless to give you a complete exposure to these kinds of questions. This is your basic question. Most of them are going to work out very similarly to this. You have to construct your diagram and assign your variables and Pythagorean theorem. But let me just show you one thing. When I drew it, I said Ada is here and Ian lives 20 kilometers north. And I said, I don't know how long they're running for, but let's say Ian runs this far and then we yell from the helicopter, freeze. Well, really, guys, and then this became 20 minus 8t. And this was the diagram that we created when we did the question. And this was 6t and this was d. But here's the alternative. If Ian lives up here and Ada lives down here, how do we know that Ian didn't run this far? And this whole distance is 8t. How do we know he didn't get past her house while he was running at a pretty good clip, 8 kilometers an hour? And if you did that and Ada was running this far, and that's 6t, your right triangle potentially could have appeared this way. But here's the cool part. Remember that you make a right triangle and you call the distance between them d. There's the variable representation of that side. We need a variable representation of this side of the triangle. Now the whole thing the whole distance was 8 kilometers per hour times t hours. This distance up here is 20. So what are you going to get for the algebra of this part? It's the whole, which is 8t, minus the 20. The whole thing is 8t, take away the 20, and that leaves you with this piece. Whereas up here, you see that piece was the whole was 20, minus the 8t, leaves 20 minus 8t. And look at the difference between the two of them. One is 20 minus 8t, the other is 8t minus 20. They're opposites. Now we use Pythagorean theorem up here. So obviously we would do the same thing here. And the only difference between it, you would think, oh my goodness, we're getting a different equation, but we're not. Because remember that these two expressions are equal. It's like saying 7 squared versus negative 7 squared. If you have opposites that are being squared, you get the same answer. If you have a minus b that's being squared, you would get the same answer as b minus a being squared. So the point is, when you do the DVT question, you might say to yourself, oh my goodness, which one should I do? I don't know which one it is. And I'm saying you can't go wrong, whichever picture you create. I always create this one. That is, I never have them quite reach that point. Once you figure out t, and once you know the actual distances that each person ran, you can then reconstruct the diagram with reality. For example, let me go back. When I figured out how far Ian ran, he ran 12.8 kilometers because I took the time that we figured out and multiplied it by his speed. If this is 12.8, then obviously he has not reached your house yet because the whole thing is 20. And so the reality of what the numbers give you then let you go back to see if your diagram was correct. But if your diagram was incorrect, no big deal, because you still have the right answer. You might fix up your diagram so that it makes more sense. But my suggestion is do it this way, because 90% of the time this is just easier and cleaner. And then you will see that whichever way you do it, you will get the same answer, but that way you don't freak out a little bit. And so you can see the homework is here. You need to do those questions, and then we are not doing other kinds of optimization questions, so that will complete the types, and we'll have an evaluation this Friday, so that gives you this whole week to nail all of these types, ask questions, and then we'll give an assignment on the Friday.